Today I will show you the result what we got after the test, how we are going to utilize that test for finding the maximum stress modulus other things. So I have already explained you that the corrected displacement, this corrected displacement or the displacement of the position, the true displacement of the specimen, okay, that is equals to the displacement what we got from the test minus the displacement of the machine. Okay, how we are getting the displacement of the machine, that I already explained. That is a compliance what we got when we have done the test without putting any specimen, or when we have done the test with the grips only into the force at that position. So now we are going to first find the compliance. Okay, we have already shown you in the video. Now I am going to in the results. Okay, in the compression, this is a compliance correction data. What I got from the machine. So I got the force position. You can see there is some forces which is not required because this is the 000. This will not help us. So I am just going to delete this part. Yes, I am deleting some extra because it is having some extra data also. So just I am giving 100 Newton of preload. Okay, that you will come to know easily. Okay, before deleting it, just I want to show you the graph. Then you will come to know why I am deleting it. Insert chart. This is the chart. This is select data. Add 1. In X, I want the position. In the Y, I want the force. This is the force and position what we get from the test directly from the machine. So you can see up to here this data is useless for us. This is a force. We have gone up to the 4000 Newton, and up to here these results are waste because this is not giving anything, just it is aligning the grips. We have given a very small displacement rate. So I'm just going and delete this part. So actually I know that is happened there, so that's why I have just delete that part. Now to find the stiffness, that is the slope, just I am shifting it actually. So I am saying absolute 0, and that is also in mm. Okay, what is that? Is equals to this position minus of 0.4. I made this position as 0, or I have just simply shifted. Okay, delete. Due to the gap it is not calculating. Now it has calculated in the same curve. Okay, in the same curve what I am going, select data, add compliance curve. Compliance curve, X is this absolute position, Y is the this force. Now you can see this curve has shifted, but I have had shifted it little bit more because it has shifted just more than that, more than 0. It should be touched at the 0. Okay, so that's not a big problem. So now we are going to find the slope of this equation. The slope of this curve will give us the stiffness of the machine. Okay, we are just going at trend line. In trend line, we are saying display equation on the chart. First of all, I want the linear. Okay, trend line is linear and I want the display equation on the chart. Okay, so trend line is linear. So we have got, you can see this is a trend line, you can see the, okay, or we can go for the legend. When we gone for the legend, then you have come to know that three curves are there. One which is the original curve, but I have shifted with the compliance curve, and when I have even shifted, so there is a best fit curve, and the equation for this best curve is this one. So the stiffness capital K is equals to 12555, okay, Newton per mm. Okay, what is the compliance? Compliance is equals to, I am writing here, compliance is equals to 1 divided by of 12555. Okay, that is 7.96 into 10 the power 5 millimeter per Newton. So we got the compliance like this. Okay, now we got the compliance. Now we can go and do our analysis. Okay, that you should write it somewhere so that it will be easy for you whenever I am doing for the other things. So I will use this compliance value for my calculation. Okay, so I'm going in the compression test, and I have shown you the test with the natural composites. With the natural composite, I have shown you the compression test. Okay, so these are the results what I got from the machine. So again, actually I know, that's why I'm again deleting some extra data. Up to 15 Newton I'm deleting. Okay, up to 15 Newton. This is, I have already done the tested, so I know okay, up to 15 Newton that this data is not required to shift. So this is the force, this is the position, but I have to correct this position because we know this absolute position or absolute zero we are marking, the absolute position we are saying it, or it is in mm. Okay, it is in mm. Now first, what is this absolute position? That is this equals to minus 0.321, that I have shifted zero position with this force. Okay, now I have to correct it because this position is having the values of the displacement of the machine also. That how I will do that? Compliance corrected value, mm. Okay, that is also in millimeter. Compliance corrected, how we are doing the compliance corrected? That is, it is equals to the tested position value, tested displacement, minus, sorry, minus the compliance. What was the value of compliance? 7.96 into 10 the power minus 5. Okay, this is the compliance into of, this is the displacement position at the same position what the force is there. So we have got the compliance correction. So we got the actual displacement of the specimen. Okay, I am again telling you that is the displacement of the test displacement minus compliance into of force. Okay, now I am going to draw the curve for you. Select data, add sample 1 x. In the x I am going to draw this one. This time I am drawing the force displacement curve. Soon I will show you the stress strain curve also. position. So this is the force versus displacement. Okay, that you can go here, click here, you can see the legend also, you will see the S1, and whenever you go it here, you can go for the access title. When click it, it will come. Then I can say okay, I can say this is the compressive stress actually in megapascal. Now, sorry. This is the force in Newton. This is the force in Newton. This is the position in mm. Okay. Now I am going to draw the stress strain curve. For drawing the stress in megapascal, just bigger, smaller itself. So for getting the stress, that is equals to force by cross-sectional area. The cross-sectional area was 50.12 into something similar, 49.68. And click it here. We got the stress. What is the strain here? Strain is mm per mm. Okay. The value of strain is corrected position divided by of the thickness of the, that is 22.16. Okay. Now I am going to draw the stress strain curve. Insert, select data, S1. In the X, I am going for the strain. In the Y, I am going for the stress. Okay. So you can see legend, axis title. So this is the curve here for the stress versus strain, that is the compressive stress megapascal. Okay, and here this is the strain mm per mm, strain mm per mm. Okay, so here what we have to do, we have seen that we have plot the position, we have plot the stress versus the strain curve. Okay, while explaining the types of the curves, first of all we are going and saying what is the maximum strength of the curve, that is a compressive strength. Sorry, I have gone for the strain maximum. I'm saying the maximum stress. We can see the 2.03 megapascal is the maximum compressive stress, and that we are getting somewhere here, or that is we can say it's the ultimate strength or the yield strength, because we can say here the yield strength, because in the ultimate it should fail, so but it's the maximum strength. Okay, so in the compression generally we are called it the ultimate itself, because after that it has start to fail. Okay, in this curve, but in the explanation I have told you that this is the toe reason, which is not useful for us. We cannot go and find the uh, modulus by using this. We have to use this reason. So what we will do, in actual, you can go it here, you can see this value, you can see, this value. Okay, this is having a value of 0.09 of strain. So you can go from this value up to this value, you can take this data separately and put it and you can go and plot the trend, uh, the line trend or the linear plot, and you will got the slope of this equation, and that will be the modulus or the Young modulus of the material. Okay, so this is one of the curve what I want to show you. The another material what I have tested is the acrylic, so I'm interested with the acrylic also. Okay, I'm going in the this machine, and okay, this is the acrylic data is opening. So this is the position versus force, this position versus force, you can see it here. Okay, so again I am going, I'm deleting the first up to 10 Newton. I am just deleting the data because that is not required, that is delete. So cells up. Okay, and we know already this is a position, we know we have to go first absolute position. After the absolute position, in absolute I want to make it capital, absolute position, then we will go for the corrected position, that is also in the mm. Okay, so how we will get the absolute position, that is this position minus of 0.006, this we got the absolute position. After that the corrected position is absolute position minus compliance. Compliance is 7.96 into 10 the power minus 5 into the force. We got the compliance correct. Now, what will be the stress and strain? So, STRESS, stress, megapascal. Okay, that is equals to force divided by area. Area is 8 into of 8 mm. Okay, so this is Newton per mm square, that is, so this is the maximum stress, this is the, sorry, this is the stress, this is the strain, mm, that is equals to position divided by of its thickness. Thickness was 7.89. So we got the stress versus the strain curve. Okay, sorry, strain data. From here, we can plot the data. In the x we want to plot the strain, in the y we have to plot the stress. Okay, so here you can see our stress strain curve is this one. Okay, this is the compressive stress versus the strain curve. But first of all, I would like, at the toe region you will see there is a some different slope is there. Actually that is when the specimen is between the grip, it is adjusting because it is not exactly the flat. This curve is showing that things. So please avoid this data. You have to subtract it. Okay. That's why I was saying the you should know कि where when you will do one or two tests you will come to know how much data you have to avoid to avoid for this kind of two reason. Okay, so here you can see this is the linear elastic region of the compression. This is the plateau region of the compression, and this is the after this is the densification. So I have told you three reasons we are generally getting it. Okay, but you can get it from here. The maximum stress, you got the maximum stress is 148 megapascal. If you want a particular stress, for example you want the yield stress here. Yield stress, first of all we should define at what position we are saying that yield should go, because all this position where this force is at this stress is approximately constant and we are getting the strain. So starting of field is doing something here starting. So we are telling it the visually. Okay, but is there any rule like that in the aluminum? We are saying for the tensile testing 0.2 percentage is the we have to take the strain by shifting it 0.2 percentage, so where the yielding is happening. So is there any criteria to say that things that you have to read in the ASTM? Generally we are saying in the compressive stress कि for this percentage of strain there is this much percentage of stress is there. Okay, so thank you friend.